Hello, so this is your second phase PFA antenna design. So the basics we have got from this paper itself. So here there is a design of planar inverted F antenna for wireless applications. So first we have designed for one frequency, which is a nearly 5 gigahertz. We have designed the frequency. So here what we have done is we are trying to make it multi-modal. So what is multi-modal is that if you have one antenna, generally it will only resonate for a specific frequency, right? But when you take the antenna, these antennas they use for mobile applications, everything. So if we take the antenna that's used for mobile application, they have to resonate in more than one frequency, because in mobile you have many applications. You have Bluetooth application, you have Wi-Fi application, you have to have some like calls will take some calls, you have to call. So there are like different applications for antenna when you're considering the mobile antennas. Okay, that is in the mobile phones. So generally what happens, these antennas they don't just resonate for one frequency, they resonate on more than one frequency. That is called as multi-modality. That is antenna will resonate for more than one frequency. So we can see when you are seeing the return loss graph, you can see that there are two dips in the return loss. That means the antenna is resonating at two frequencies. Okay, so we have taken the base as this, that is the similar the equations which were used in the first phase, the same equations we have been using. So it's actually essentially I've used the same equations, then I have actually taken hit and trial method. I've used hit and trial method, like by changing the width of the length of this shorting pin, length of the patch, width of the patch, and everything. I have actually used these kind of little bit tuning kind of thing with the base values that we have used in the first place. I have tuned the antenna such that it will be resonating at 2 points. So this is actually hit and trial kind of thing. Okay, so it took a lot of time, because it takes a lot of time. Normally you have this antenna and then you have to like increase a millimeter of width or increase 1 millimeter of length or decrease it, vice versa. So we have to keep on doing it till you get the uh, antenna which is resonating at two frequencies. Okay, so if you consider the so as whenever you are considering antenna, so firstly when you're designing an antenna you need mainly three things, right? We need the resonating frequency or where you want it to resonate, and you need the substrate dielectric constant as well as substrate's width, right? So here when you're designing, there are some steps of designing. First thing you do is actual designing of the antenna, designing as in the physical design. You're designing the ground, designing the substrate, designing patch, and um, shorting pin, feed line, everything. You're designing everything, and you have radiation box. You design the physical design. After that you have to give the boundaries, and after that you have to give excitation. Fourth step is for give is that you have to give a sweep. From this point to this point you have to give a sweep, and after doing all that you will get the answer, or you can simulate the antenna, right? So let's start with the designing. So the designing, you can see that this is called as project manager. Here you can see everything will be here. What are the boundaries you have given, what are the different excitations you have given, analysis, everything, result, you will get result, everything you can see. This is actually the whole project, you can see it here, right? And this is where you can see the physical design, like you have solids, you have different kind of solids. So what are the different solids you have? See, this is radiation box, you have feed, you have inner, again you have substrate, a different kind of shapes which you have used as antenna. That is what you can see here, right? So I'll explain it one by one. Sorry. So first let's start with ground as usual. Just a minute. So this is the ground. You can see that this the portion that is below, that's the ground. So here if you double click the ground, you can see what are the different sizes I've used. So I've used 42, x is 42 and y is 20, y is 20, and I have also the position is also given 000, that is the position. So I have used that. So these equations that I've got by trial and error method, I have tried many measurements, and then I have found out that in at this particular measurements, what are measurements I have used in this design, the antenna is giving you like it is resonating for two frequencies at the same time as in same antenna. You can see in the same uh, like graph itself, you can see two resonating points, right? So this is ground. And again, if you consider, next we go to the substrate. So this is substrate. Where is substrate? Yeah, this is substrate. So the equation, everything is here. I mean equation as in the, sorry, not equation, yeah, what is the size of the substrate, what is the height is 0.8 millimeters. So you can see all of them here. So I have used a material called as Rogers RT Duroid 5880. Okay, this is kind of like you can just select it. You can see that there are different kind of materials. You can just edit it. You can find different kind of materials. So this is what I've used. Its relative permittivity is 2.2. Permittivity is 2.2, and there are many other materials, so you can select anyone. Okay, so this is what I have selected. So this was giving the best results, so I have selected Rogers. Okay, so substrate is over, and then you have to see the patch. Okay, so patch is, this is patch, right? This thing is patch. So again, if when you click it, you can see all the dimensions. So the patch, it has to be above the ground, because you can see it's not touching the, this is the substrate, the patch is not touching the substrate. You have the patch and you are actually shorting it with the ground. Okay, it is not actually touching the substrate, and it is shorted at 2 points. This is one shot, and this is actually feed line, right? So after the patch, then you have to design the short pin. So this is shorting plate. See, this is shorting plate, and you can also see what are the dimensions of shorting plate. So now we have designed the ground, we have designed substrate, right? And then you have designed the patch and the shorting plate. Now what we have to do is we want a feed line. So this is called as a feed line. So this green portion is where you're giving the input, and the input, it has to like connect to this part, and then it has to it has this whole thing, it is kind of transmission line. You are giving the input, and this input signal has to be transmitted to the patch, right? So this is actually something called as feed. So for feed, you're using copper for feed. Okay, so when you touch it, you can see that. So this is the feed means the whatever that is giving the signal to the patch is called as feed, and this is called as inner means there's something that is inside this. Okay, so the whole thing, you actually have attached, this is the feed and this is the inner, this also kind of feed only. Okay, so you can also see what the height of the cylinder, radius of the cylinder, and everything, you can see all that. So this I have chosen it as copper. So it has to be conducting, right? Whatever plate you are using, the ground and the patch as well as the feed has to be conducting. If you're giving it as Teflon or something, then it won't conduct. So that's why I've given this as copper. And this thing is an insulation kind of thing, like an insulation around the copper. Yeah, that is, so I have given that as Teflon. So this outer one, it is Teflon, it is just kind of insulation kind of thing. Okay, that is used. So we generally give an insulation to whatever transmission line you have, you give an insulation, right? So this is similar, it acts as an insulation, right? It is Teflon. Okay, so we have actually designed all that. Now what you have to do is, after all this, you have to design the port. So port is, I'll show you where the port is. Yeah, so this is the port. So here the port is in the bottom part. You can see that port is here. Here you're giving the input voltage, and it is actually connected to the feed line. So your input voltage will travel through the feed line and it will reach the patch. Okay, so this is the port. That's also, you can see it's like a circle. So what is the radius, etc., you can see here. Okay, just a minute. Yeah, so that is the basic design. And now last you have to put a radiation box also. That is very important, you always have to put a radiation box. You don't have a specific dimension for the radiation box. It has to be it should be such that the antenna should be inside, it should be inside the radiation box. It has to surround the antenna fully. You can take any dimension which is larger than that of antennas. Okay, so this is the design. So what have we done? We have designed the ground, and then you have designed the substrate, and then this the patch, shorting pin, And this is what? This is actually the feed, and then you have a Teflon outer coating. Sorry. Yeah. And then pot. Yeah. So these are the basic um, design. Like physical design of antenna is done. So after physically designing antenna, now the second step is to give it boundaries, right? So when you consider boundaries, you can see there are three boundaries here. First one is radiation boundary. So whatever radiation box you're giving, you just have to right click, and if you assign the boundary, you can assign the boundary as radiation. So the whole boundary, it will be radiation. So what happens if you don't assign? You can see that the material is also air. You have to give air. If you cannot give vacuum, because when you're giving vacuum, what happens that the radiation pattern cannot be, you cannot see it in vacuum. So we are telling the software that there is a radiation box around it which is covered in air, and you are also giving the boundary as radiation, right? So that you can see the radiation patterns. Okay. So this is the first boundary, and then you can see there is a boundary perfect E. So yeah, we have given ground, patch, as well as shorting plate. All these three, ground, patch, and shorting plate, they have to be conducting, right? So that is why three of them we are given it as like, yeah, perfectly conducting. So just click all three, then assign boundary. You can see perfect T means perfectly conducting. Okay, so there are two boundaries basically, one radiation boundary and one perfect T boundary. Radiation boundary is for the radiation box, and perfect T is for the ground, patch, as well as shorting plate, right? So now finished with the boundaries. So the third part, or the third step, is giving the excitation. So this is a port. I told you the port is below the feed line, so this is where you can find the port. Yeah. So for the excitation, you have to click the port, then right click. You can see there is something called as assign excitation lumped port. When you do that, the excitation, that is what we are giving input signal to the port. Okay, so three of the steps are done. We have designed the antenna, we have given the boundary conditions, and we have also given the excitation, right? So after that, next step you have to do is we have to give a frequency sweep. So go to analysis, and here you can see there is something called as frequency sweep. So I have given 0 to 20 gigahertz just to see where the antenna is resonating. I have taken such a large band gap. Sorry, I'll show you. 0 to 20 gigahertz. So if you see the display, you can see that 0, 0.1, 0.2. So why we are doing this linear sweep, or the sweep, is that actually the software will give these frequency in this step. Like first it will 0 gigahertz, then 0.1, 0.2. It will give these frequency to the antenna, and it will test the antenna. So whenever the antenna reaches its, or it finds its resonating frequency, it will resonate at that particular frequency. So we are just actually testing all the frequencies till we find the perfect frequency where the antenna will resonate. So that is why we are giving frequency sweep. So after frequency sweep, you have to validate this thing. This is called validation of model. So here you can see that it is validate. This thing is just warning. Warning means what happens when sometimes what two boundaries may overlap with each other. That is not a problem. It won't be any problem with the model, but it will give a warning that okay, two boundaries are getting overlapped with each other, like that. Okay. So if you are getting a red cross mark, then it means that your model is not correct. So now we are getting everything correct, and this is okay. So this means that our validation check is over, and our model is fine. You can go ahead with this model, right? After that, you just have to click this, so where you can simulate everything. So after simulation, these are the results I got. So you can see that, so the first our antenna was resonating at 5 gigahertz. Now I've made our antenna to resonate at one more frequency, which is 16. So it is resonating at 5 gigahertz and 16 gigahertz. So why I'm saying both of them are resonating? The whenever you're plotting this return loss, whenever this dip, it goes beyond minus 10 dB, it means that it is resonating. If the dip is above minus 10 dB, if somewhere dip is like this, so it doesn't mean that it is resonating. But whenever it is less than minus 10 dB, it means that this is resonating. So the antenna is resonating at this point as well as at this point, right? So you have got a multi model. Multi-modal means a same antenna resonating at two different frequencies. We have got that. Okay. And similarly, I've plotted VSWR. Here also you can check with the marker. You can take the marker and you can see it will be nearly 5. Yeah, 5. And this is it. This will be 16.2. Similar. In the similar region, you can see that VSWR is also less. Right. And there is a radiation pattern. This is the radiation pattern. And this is a 3D polar plot. Yeah, you can check the 3D polar plot. So wherever this red sign means that it is very much like it is radiating very heavily, or it's very good at this red part, and the blue part means that there is no radiation. So you can see that around this region there is radiation, and in between the radiation is less. Okay, so this is the radiation pattern we are getting. Okay, so that is how you design a PIFA antenna for two frequencies. So the first phase we only did for one frequency. So this phase, rather than just like doing it for some other frequency, it is better. You can show that you are, because this antenna is used in mobiles and everything, right? So you can show that the antenna, we have designed an antenna, same antenna is resonating for two different frequencies, which is like 5 and 16 gigahertz is used for two different applications. Okay, so we have designed a multi-modal PIFA antenna. Okay.